So when the elasticity is 1, that means that demand is in equilibrium. And we're maybe at a maximum. What we actually know is basically that something has a critical point at this place. If you're less than 1, you should increase. If you're greater than 1, you should decrease or whatever. At 1, the thing is at a critical point. We made a big deal before spring break about just knowing you're a critical point isn't enough to know that you are the maximum. We're not likely to actually think about that in these terms here for the elasticity and other Goldilocks cases. We usually just assume that you actually are at a maximum. And the problems won't have, like that first problem we did had instructions to verify the thing is a maximum. These problems will usually not say that extra piece of work. So far, I guess a big question to ask is, what does any of this have to do with calculus? Like, the whole big deal about optimization was taking derivatives of things, and this definition of elasticity has no derivative of anything in it. Well, here's the place where I say, well, that's actually only one of the definitions of elasticity. The elasticity we just talked about was the discrete case. Discrete meaning you only have finitely many points. We talked about that, saying at this sales number and at that sales number, we only knew 2 facts. And this formula was elasticity is negative, percent change in Q over percent change in P. This is the first formula for elasticity we used. And discrete means we use this when we're given a couple points. Like how when we were trying to take derivatives of things and we only had a chart, we would just take a slope and say that's the chart. Or I guess we actually took 2 slopes and took their average. The continuous case is when you know all the values. We're going to use this when we have a function. The function is a full demand curve. And what's this formula going to be? Think about how you found the percent change in Q. You took how much was the change in Q, and you divided by how much Q there was. And to change that to a percent, you would multiply that by 100. How do you find the percent change in P? You take how much was the change, divide that by the original P value. You multiply that by 100. Well, the hundreds cancel. You get delta Q over delta P. The way you divide fractions is you multiply by the reciprocal. So we have the top, delta Q over Q, times the reciprocal of the bottom, P over delta P. If you rearrange the order of these things, you get delta Q over delta P times P over Q. All these percent changes are supposed to be thinking about a small change in price and a small change in quantity. So we're assuming these things are small, which makes this close to the derivative. Oh, I should have said there was a minus sign out here the whole time. When this becomes a derivative, because the thing is small, you get dq dp times P over Q. You get these 2 formulas. This one is just the change in Q over change in P. I usually remember it as the Q goes on top. Except in this version of the formula, there's 2 fractions, and the things on top are different. Well, the Q goes on top for the important fraction. Which one's the important fraction? It's the derivative one, because we're in a calculus class, so that's the important one. And it's backwards for the other one. I don't know if that's helpful for anybody but me. But that's how I remember this. The formula for elasticity, if you have a whole formula, is that it's negative dq dp times P over Q. Let's try using this out. Here's an example. When I sell, what do I sell? I guess okay, if my demand function, demand function, is Q of P equals, maybe it's 500 e to the negative 0.3 P. This is an exponential decay function. It is decreasing. Sales go down as price increases. We're in the rational model. Should be a decreasing function. What's elasticity? At a price of, or what's our elasticity function first? What's elasticity at a price level of 250? Is demand elastic or inelastic at that price? To increase revenue, would we increase or decrease the price? And then part 3, what price maximizes revenue? So let's do that. How do I find my elasticity function? I have a formula for it. Elasticity is negative dq dp times p over q. A thing to pay attention to is when I'm finding dq dp, that means take the derivative of q with respect to p, I need my q to be written as a function of p. If you have your p as a function of q, you should probably solve for q before you try and do the derivative thing. So I need negative, what's the derivative of q? I need to look at this function and take the derivative. 500 is a constant out front, stays out front. E to the derivative of e to the something is e to the, leave the inside alone. Multiply by the derivative of the inside. What's the derivative of negative 0.3p? It's negative 0.3. Times, what's p? Q is a function, p is a variable right now. So p on top is just a variable. Q on bottom is the formula we have for q, 500 e to the negative 0.3p. A thing that's a pain to keep track of is I plug in for q, I don't plug in for p, because p is being a variable right now, not a function. What is this? I got 500 over 500 cancels. I got e to the negative 0.3p over e to the negative 0.3p cancels. I have negative times negative cancels. There's like a miracle of cancellation here. Our formula for e turns out to be the very simple formula 0.3p. This happens for exponential decay functions. Don't feel weird if this miracle of cancellation doesn't happen for other examples. Here's our elasticity function. Here's the answer to part 1. Part 2 says, what is it at a price of 250? I ask, what's e of 2.5? It's 0.3 times 2.5. What's 0.3 times 2.5? 3 times 25 is 75. Move the decimal back 2 times, so 0.75. It's less than 1, so demand is inelastic at that price. And what does that mean? Let's see, the top is smaller than the bottom. Big change in price has small change in sales, so it's safe to hike up the price. Revenue increases. When price goes up. Did I get that right? I always screw this up. When demand is inelastic, raise the price to increase revenue. Yeah, that's correct. Part 3, what price maximizes revenue? Notice that we didn't say the sentence of show that it's a max. Like that sentence that I had on the first example today wasn't there. So I don't actually have to verify that my thing is a maximum. Just find the thing and we'll just trust that it is a maximum. How do I find my thing? I know that revenue should be maximized when elasticity is 1. I take my formula for elasticity and ask, does it ever equal 1? Does 0.3p ever equal 1? So p is 1 over 0.3. That's 10 over 3. That's 3.33. Revenue is maximized. At a price of $3.33. Yep,